Hi, I'd like to dedicate this video to the students and teachers of Ukraine. May you know peace, independence, and sovereignty. I will be solving this problem that comes from the Ukraine Math Olympiad of 2021. It's designed for 10th grade students, and it was the first question on the test. Here's the problem. Alexey and Bogdan play a game with two piles of stones. In the beginning, one of the piles contains 2021 stones, and the second is empty. The players alternate, and in each move, the player has to pick up an even number of stones, more than 0, from one of the two piles, transfer half of the stones taken to the other pile, and the other half is discarded from the game. A player that cannot make a move loses. Who will win this game if both try to win and Bogdan begins? One little curious thing about this is they have two players, A and B, and instead of having player A start, Alexey, they have player B, Bogdan, start. Turns out that a longtime coach of the Ukraine National International Math Olympiad team is named Bogdan Rublov. So that may have been a nod in that direction. First, let's try to understand this game. You have two piles of stone. At the beginning, there's 2021 stones in one stack and the other is empty. So the first person who moves will have to take an even number from one of the piles. And since it's non-zero, it has to be from the 2021 pile. And so let's say that they take a pile this big. Well, they have to cut that in half. Part of it will go over here. And the other part is just discarded. So it's just gone. So we end up with one pile like this, and the other small pile like that. And then the next person takes an even number. So they could take from the first pile, cut it in half goes here, and then the other half just discarded. Or they could take from the small pile. They could take a tiny sliver, or they, in fact, at any time, they could take one whole pile if it's an even number. They cut it in half. Half goes over here. And half go away. And they start taking turn. Assuming they both play the best game they can, is there a known winner? Is there a strategy so that one side wins all the time? How can you lose? If I have any stack with at least 2, I can just take 2, put one in the other stack, and one go away. If there's a 2, I'm not going to lose. So the only way to lose is that there is not a 2. Lose if I have a stack of 1 and 0, or a stack of 0 and 1, or a stack of 1 and 1. I'm going to write this with bracket notation. 1, 0, meaning there's one stack with a 1 and the other stack with 0. This one is 0, 1, and this is 1, 1. 1, 0, and 0, 1 are the same. Because in terms of moving stones, it really doesn't matter which one is which. We can treat these two stacks as the same kind. If I wish to win, so this is the winner's wish list. Let me deal with the 1, 0 situation first, and then we'll go to the 1, 1 situation later. The winner's wish is to have the loser get stuck with 1, 0. How do I get the loser stuck with 1, 0? If I have 0, 2, then I can take 2 from the 2, put 1 here, and 1 gets discarded. I want 0, 2 so that I can impose 1, 0 onto the loser. Obviously, the loser will try to avoid giving me 0, 2. So how can I force the loser to give me 0, 2? If I can force the loser to have 2, 1, then they have no choice but to take 2 out of the stack of 2, give 1 here and 1 discarded. If I can impose 2, 1 onto the loser, they have no choice but to give me 0, 2, which I then give them 1, 0, and I win. Yay. Okay, great. What can I start with that would get me 2, 1? I can start with 1, 3, because then I can do take 2 out of here, 2 out of 3, put 1 here and 1 go away. That will get me 2, 1. Another way of getting 2, 1 is if I have 4, 0, I take 2 out of 4, put 1 here and 1 go away. Then I end up with 2, 1. That's great. How do I force the loser to give me 1, 3 or 4, 0? Well, for 1, 3, if they have 3, 2, and then they have 2 choices. One is they take 2 out of 3, give 1 here, and 1 go away. That would end up with 1, 3. Well, they're not dumb. They may not do that. They may do 2 out of here, put a 1 here, and put a 1 go away instead. Well, that doesn't help because then they end up with 4, 0, or I end up with 4, 0, and I'm happy with 4, 0 as well. So far, I'm getting what I wish. What can I start with that allows me to impose 3, 2 onto the loser? I could start with 2, 4. Then I just take 1 here and 1 go away. Now let me change the color of this so we can keep track. So far what I'm saying is if I can have 2, 4, then I can impose 3, 2 on the loser. From 3, 2, the loser has no choice but to give me either 1, 3 or 4, 0, both of which I can end up with 2, 1 for them. And from 2, 1, they have no choice but give me 0, 2. And from 0, 2, I can give them 1, 0, and then I win. Let's do one more. What kind of number does the loser get stuck with that would force them to give me 2, 4? Sounds like 4, 3. If they have 4, 3, and they take 2 out of here, out of 4, and put 1 in 3 and 1 away, then I end up with 2, 4, and I'm happy with that. Of course, they're not dumb. They're not going to do that. They may try to take all 4 out of the first and put 2 in here and 2 go away. Then that way they end up with 0, 5, or I end up with 0, 5. Oh, but that's okay. If I have 0, 5, take 4 out of 5, put 2 here, 2 go away, and I end up with 2, 1, or I put 2, 1 on them. Yeah, if they give me 0, 5, then it doesn't help them because that's a number in this row. 0, 5 will help me get 2, 1. 2 go over to the empty stack, 2 go away, and I end up with 2, 1. How about if they take 2 out of the 3 stack instead and put 1 in here and 1 go away? Then I end up with 5, 1. But it's okay. 5, 1, I put 1 in here and 1 go away. Then I end up with 3, 2. So far I have this. If I can impose 4, 3 on the loser, they have 3 ways to move and all 3 ways are good for me. I can land them on 3, 2 or 2, 1. Either way, they can do what they can and then I can give them another loser situation. So all the positions, all the configurations in the first column are the configurations I want to impose on the loser so I can win. I see a pattern already. I see 1, 0, 2, 1, 3, 2, 4, 3. I see that the configuration on the loser side has a difference of 1. I sort of suspect the next one would have been 5, 4, 6, 5, 7, 6, 8, 7, etc. That's what I see, so that's what I speculate. And I'll see if I can prove this. So I speculate a configuration of n plus 1 comma n will lose. In order for this configuration to lose, I need two things. One is, as soon as I can stick the loser with it, they can't get out of it. Specifically, they cannot kick it back to me. Because if they can kick it back to me, then obviously it's not a losing configuration because we can't both lose. It's only a losing configuration. It stays in one side. Therefore, this leads to two things I need to prove. I need to prove, number one, once you have n plus 1 comma n, no matter the next move, the new difference will not be equal to 1. They cannot kick it back to me. They can get out of it temporarily because now it's my turn again, right? Thus, a second thing that I need to prove is once they get out of it, I can put them back. Ha! Once I have n plus k in, where k is greater than or equal to 2, there is a move that results in new difference equal to 1 again. If I can prove both 1 and 2, then what it means is as soon as a player can impose n plus 1 comma n onto the other player, that person wins. Because the loser will try to get out of it, I kick them back. And they try to get out of it, they put them back. And every time we do that, the total decreases, right? Because there's at least one stone that gets removed each time. So eventually I will end up with 4-3, 3-2, 2-1, and 1-0, and I win. Let's take a look at number 2, how it can happen. I have a stack and a smaller stack, and the difference is large. It's not 1. If I want the difference to be 1, the short stack will get some, and I want the tall stack to be exactly 1 above that, knowing that there's another stack just like this that got discarded. So it sounds like I should do something like there's 1 here, and then of the remainder, I should divide it in 3. 1 part stays, 1 part goes here, and 1 part goes away. So the even number that I'm taking out here is, this is what I take out. I take out that much. It sounds like I'm taking out the difference between mn, but I save 1 to stay. I take it in third, 2 times that. 1 piece goes to the short stack and 1 piece goes away. That means because of the dividing by 3, it sounds like I need to pay attention to mod 3. Because of the division by 3, I need to pay attention to the remainder, mod 3. I want to make sure the numbers are integers, right? We're not talking about half a stone or anything. All right, so that's my strategy. This is my speculation. I'm hoping to prove it by proving number 1 and number 2. And while doing so, I need to pay attention to modulo 3. Solution then. First, let's define. Let bracket mn denote the situation where one pile has m stones and the other pile has n stones. And since it doesn't really matter which way I go, which pile is listed first, I might as well list the big pile first. So without loss of generality, m is greater than or equal to n. All right, claim 1. If m minus n is equal to 1, then no matter next move, new difference is not 1. Proof of claim 1. I have n plus 1 in n. I need to take an even number. So I need to take 2k from somewhere. So let's say I take it from the large pile. So if I take 2k from n plus 1, then the new configuration will be n plus 1 minus 2k. I take 2k from n plus 1. Half of it I put it in the other pile, and the other half I discard. So next pile is n plus k, whereas k is greater than or equal to 1, which means this will be the bigger pile. And so the new difference is n plus k minus n plus 1 minus 2k, like this. And that is equal to, the n's cancel, is equal to 3k minus 1. And because k is greater than or equal to 1, then 3k is greater than or equal to 3, and then minus 1 is greater than or equal to 2. So this whole thing is greater than or equal to 2. Oh, look, there's a 3k here. So also the new difference is going to be negative 1 mod 3. All right, that's the situation if we take 2k from the n plus 1 from the bigger stack. What if we take it from the smaller stack? If we take 2k, k greater than or equal to 1 from n, so it used to be n plus 1 comma n, like this, then the n stack is smaller. The n plus 1 stack gets bigger by k, and then k gets thrown away. Therefore, the new difference is going to be n plus k plus 1 minus n minus 2k, like this. And that is equal to 3k plus 1. This is greater than or equal to 4, because k is at least 1. And also, new difference is congruent to 1 mod 3. In the proof of claim 1, I actually got a better result. And that is, once I have n plus 1 and n, then no matter what move, the next difference is going to be greater than or equal to 2, and is equal to either 1 or negative 1 mod 3. Claim 2. From mn, where m minus n is greater than 2, and m minus n is congruent to 1 or negative 1 mod 3, I can move so that the new difference is 1. Proof of claim 2. I already sort of drew this picture already, but let's do it again. Let's say that I have m here and have n here. Then I want to keep a slice of 1 here. I divide the remainder into 3 pieces. I take out 2 of these. 1 piece goes away and 1 piece goes to the shorter stack. So if this is m and this is n, then it sounds like I should take m minus n minus 1. So that's this part right here. And I should take 2/3 of that, equals to some 2k, and then k goes to n, and k is discarded. This tells me that k is equal to m minus n minus 1 over 3 generally. And I'm going to need to have to worry about making sure that it's a nice integer. So it sounds like this is where I really need to work in modulo 3. Case 1. The difference is congruent to 1 modulo 3. That means one stack is n plus 3k plus 1, and the other stack is n, where k is, also the difference is at least 2, so that means k is at least 1. This is actually the easy case because I want to keep n plus k plus 1 here and n plus k here. So it sounds like I should take 2k from first pile. Then the first pile becomes n plus k plus 1. The 2k, k goes to n, and the other k is discarded. So the next stack is n plus k, and the difference equal to 1. Case 2 is the difference is congruent to -1 mod 3. And the difference is, again, greater than or equal to 2. So that means I have n plus 3k plus 2 and n, where k is greater than or equal to 0. Then again, I need to take out about 2k. If I take out 2k, then I have n plus k plus 2 and n. Oh, then I'll just move one more over. So yeah, take 2k plus 2 from the first pile. Then k plus 1 goes to the n, and k plus 1 is discarded. The new stack will be n plus k and n plus k plus 1. So again, the difference is 1. Not only I have proven case 2, but I also have a strategy in mind. There is a winning strategy. We have 2021 and 0. 2021 is congruent to -1 mod 3. So I'm going to use the strategy here of taking 2k plus 2. This is 3 times 673 plus 2. So here's my k. So Bogdan will take 2 times 673 equals 1346, and then plus 2. So that results in the first stack now down to 673. And then from this, 674 goes to the 0, and 674 is discarded. And I end up with 674. So Bogdan got 673 and 674. Every time Alexey moves, the result will be n plus 3k plus 1 comma n, or n plus 3k plus 2 comma n. Then Bogdan should, for the 3k plus 1 is case 1 up here. Bogdan should take 2k from the first pile, from the large pile, the larger pile. And in this case, Bogdan should take 2k plus 2 from the larger pile. Yep, 2k plus 2. Therefore, Alexey will always be stuck with n plus 1 comma n. And since the total decreases all the time, eventually Alexey ends with 1-0 and loses. So the conclusion is Bogdan wins. First mover wins. One more thing I need to take care of is back here. We said there are 3 ways to lose. 1, 0, 0, 1, which is the same thing, or 1, 1. Using our strategy, we really don't need to force the loser to get 1, 1. But what if the loser can impose 1, 1 on me? How do I avoid that? Well, I avoid that because in proving claim number 1, remember that we figure out the difference that the loser can impose on me will always be either 1 or -1 mod 3. It's not going to be 1, 1 because 1, 1, the difference is 0 mod 3. But we do need to write that into our solution. So let's add that to the bottom here. Note, arriving at 1, 1 also loses, comma, and is the only other way to lose. But second mover cannot force 1, 1 because, comma, once at n+1 in, next move only results in a difference of 1 or -1 mod 3. So 1, 1 is not possible. QED. I hope you like the problem and the solution. It's a great problem. I'm dedicating this video to the students and teachers of Ukraine. May they know peace, independence, and sovereignty. Thanks for watching. Bye.